Bohr's model of an atom. An atom is made up of three particles: electrons, protons, and neutrons. Electrons have negative charge, protons have positive charge, whereas neutrons have no charge. They are neutral. Due to the presence of equal number of negative electrons and positive protons, the atom on the whole is electrically neutral. The protons and neutrons are located in a small nucleus at the center of the atom. Due to the presence of protons, nucleus is positively charged. The electrons revolve rapidly around the nucleus in a fixed circular paths called energy levels or shells, denoted either by the numbers 1, 2, 3, 4, 5, and 6 or by the letters K, L, M, N, O, and P, counted from the center outwards. Each energy level or shell is associated with a fixed amount of energy, the energy increasing from the center outwards. There is no change in the energy of electrons as long as they keep revolving in the same energy level. Advantage: Bohr's model of an atom explains the stability of atoms by saying that there is no loss in the energy of revolving electrons of the atom as long as they keep on revolving in the same energy level, due to which the atoms remain stable. Mass number: the total number of protons and neutrons present in one atom of an element is known as its mass number. For example, one atom of sodium element contains 11 protons and 12 neutrons. So, the mass number of sodium is 11 plus 12 equals to 23. Similarly, a normal carbon atom has 6 protons and 6 neutrons. So, the mass number of carbon is 6 plus 6 is equals to atomic number. Atomic number: the number of protons in one atom of an element is known as atomic number of that element. For example, one atom of sodium element has 11 protons in it. So, the atomic number of sodium is 11. Similarly, one atom of carbon element has 6 protons in it. So, the atomic number of carbon is 6. Isotopes. Isotopes are atoms of the same element having the same atomic number but different mass number. The isotopes of an element have the same atomic number because they contain same number of protons and electrons. The isotope of an element have different mass numbers because they contain different number of neutrons. Here is an example of isotopes. All the chlorine atoms contain 17 protons. So, the atomic number of all the chlorine atoms is 17. Now, some chlorine atoms have 18 neutrons, whereas other chlorine atoms contain 20 neutrons. Chlorine atoms can therefore have mass number of 17 plus 18 is equals to 35, or 17 plus 20 equal to 37. Thus, chlorine has two isotopes of mass number 35 and 37 respectively. The two isotopes of chlorine can be written as Cl 3517 and Cl 3717. Isobars. Isobars are the atoms of different elements having different atomic numbers but the same mass number. Isobars have different number of protons in their nuclei, but the total number of nucleons, means protons plus neutrons, in them is the same. An example of isobars is argon, symbol Ar 4018, and calcium Ca 4020. This is because argon and calcium are atoms of different elements having different atomic numbers of 18 and 20 respectively, but they have the same mass number of 40. Uses of isotopes. Radioactive isotopes such as uranium 235 are used as a fuel in nuclear reactors of nuclear power plants for generating electricity. Second, radioactive isotopes such as cobalt 60 are used in the treatment of valency by taking the examples of silicon and oxygen. The valency of an element is defined as the number of electrons lost, gained, or shared by one atom of the element to achieve the nearest inert gas electron configuration, means having 8 electrons in the outermost shell, or 2 electrons if the outermost shell is K shell. First example, valency of silicon. The atomic number of silicon is 14, so it has 14 electrons in its atom. The electronic configuration of silicon atom will be K2L8M4. Thus, the silicon atom has 4 electrons in its outermost shell, which is M shell. Now, a silicon atom can neither lose 4 electrons nor gain 4 electrons to achieve the octet, means 8 electrons in the outermost shell, due to energy considerations. So, a silicon atom will share its 4 electrons with the 4 electrons of atoms of other elements to achieve the 8 electron inert gas electron configuration. Since one silicon atom shares 4 electrons to achieve inert gas electron arrangement, therefore the valency of silicon is 4. Next example, valency of oxygen. The atomic number of oxygen is 8, so it has 8 electrons in its atom. The electronic configuration of oxygen atom will be K2L6. Thus, the oxygen atom has 6 electrons in its outermost shell, which is L shell. Now, an oxygen atom having 6 outermost electrons can gain 2 electrons from some other atom to achieve inert gas electron configuration of 6 plus 2 equal to 8 outermost electrons. Since one atom of oxygen can gain 2 electrons to achieve the inert gas electron configuration, therefore, the valency of oxygen is 2. Model of an atom. Rutherford's model of an atom. An atom consists of very small positively charged nucleus containing all the protons and neutrons at its center, with negatively charged electrons revolving around it in circular paths with high speeds. The electrostatic attraction between the positively charged nucleus and the negatively charged electrons hold the atom together. Third point, the number of positive proton is equal to the number of negative electron, due to which an atom is electrically neutral. Fourth point, almost the entire mass of an atom is concentrated in the nucleus. Fifth point, most of the atom is empty space. Limitation of Rutherford's model of an atom. Rutherford's model of an atom could not explain the stability of atom because the accelerated circular motion of revolving electrons should make them lose energy by radiation, fall into the nucleus and make the atom to collapse quickly, which does not happen at all. That's the limitation of Rutherford's model of an atom. Thomson's model of an atom. Thomson model of an atom. An atom consists of sphere or ball of positive charge with negatively charged electrons embedded in it like the seeds in a watermelon. Second point, the total positive charge on the sphere is equal to the total negative charge on the electrons, due to which an atom is electrically neutral. It has no overall positive or negative electric charge. Limitation of Thomson model of an atom. Thomson model of an atom could not explain the results of alpha particle scattering experiment carried out by Rutherford. The limitations of Rutherford's model of the atom. Answer. The major limitation of Rutherford's model of atom is that it does not explain the stability of the atom. This will become clear from the following discussion. In Rutherford's model of the atom, the negatively charged electrons are revolving around the positively charged nucleus in circular paths. Since the direction of motion of electrons moving in circular paths changes continuously, therefore, the motion of electrons moving around the nucleus is accelerated. Now, according to the electromagnetic theory of physics, the charged electrons undergoing accelerated motion around the nucleus will lose their energy continuously by radiation. The speed of electrons will therefore go on decreasing. They will be attracted more strongly by the oppositely charged nucleus. They will come more and more close to the nucleus and ultimately fall into the nucleus by taking a spiral path. This should make the atoms very unstable, due to which the atoms should collapse quickly. This, however, does not happen. The electrons do not fall into the nucleus. Atoms are very stable and do not collapse on their own. The Rutherford's model, however, does not explain this stability of an atom. So, this is the limitation of Rutherford's model. The limitations of J.J. Thomson's model of the atom. J.J. Thomson's model of atom could not explain the result of alpha particle scattering experiment carried out by Rutherford. That is, J.J. Thomson model of the atom could not explain why most of the positively charged alpha particles pass straight through the gold foil. A few alpha particles are deflected through small and large angles, whereas very few alpha particles completely rebound on hitting the gold foil and turn back on their path. Second point, J.J. Thomson's model of atom was just based on imagination. It did not have any experimental evidence in its support, like the Rutherford's model of the atom. So, this is the limitations of J.J. Thomson's model of what do you think atom would be the observation if the alpha particle scattering experiment is carried out using a foil of a metal other than gold? Answer. If the foil of a heavy metal like platinum having a very heavy nucleus is used, then the observations in the alpha particle scattering experiment would be the same as that in the gold foil experiment. Second, if, however, the foil of a light metal like lithium having a very light nucleus is used, then the fast moving heavy alpha particles may even push the light nucleus aside and may not be deflected back. That would be the observation if the alpha particle scattering experiment is carried out using a foil of a metal. On the basis of Rutherford's model of an atom, which subatomic particle is present in the nucleus of an atom? Answer. Rutherford's model says that an atom has positively charged nucleus. So, the subatomic particle present in the nucleus of an atom is proton, which carries positive charge. Explain. On the basis of Thomson's model of an atom, explain how the atom is neutral as a whole. According to Thomson's model, an atom consists of a sphere or ball of positive charge with negatively charged electrons embedded in it, like the seeds in a watermelon. The total negative charge of electrons is equal to the total positive charge of a sphere. These equal and opposite charges balance each other, due to which an atom becomes electrically neutral as a whole. If an atom contains one electron and one proton, will it carry any charge or not? Answer. No. The atom will not carry any electric charge. This is because the electron has one unit negative charge, whereas one proton has an equal and opposite one unit positive charge, due to which the net charge on the atom is 0. What are canal rays? Explain it. Answer. Canal rays, or also called as anode rays, are streams of positively charged particles which move towards the negative electrode, also called as cathode electrode, in a discharge tube. When high voltage electricity is passed through a gas at very low pressure taken in the discharge tube. Suspension. A suspension is a heterogeneous mixture. The size of solute particles in a suspension is quite large. It is larger than 100 nanometer in diameter. The particles of a suspension can be seen easily. The particles of a suspension do not pass through a filter paper, so a suspension can be separated by filtration. The suspensions are unstable. The particles of a suspension settle down after some time. A suspension scatters a beam of light passing through it because its particles are quite large. Sol. Thank you. Or also called as colloid. A sol or colloid appears to be homogeneous, but actually it is heterogeneous. The size of solute particles in a sol or colloid is bigger than that of true solutions, but smaller than that in a suspension. It is between 1 nanometer and 100 nanometer in diameter. The particles of most of the sols or colloids cannot be seen even with a microscope. The particles of some of the sols or colloids can, however, be seen through a high power microscope. The particles of a sol or colloid can pass through a filter paper, so a sol or colloid cannot be separated by filtration. The sols or colloids are quite stable. The particles of a sol or colloid usually do not separate out on keeping. A sol or colloid scatters a beam of light passing through it because its particles are fairly large solution. Thank you. Or also called as true solutions. A solution is a homogeneous mixture. The size of solute particles in a solution is extremely small. It is less than 1 nanometer in diameter. The particles of a solution cannot be seen even with a microscope. The particles of a solution pass through a filter paper, so a solution cannot be separated by filtration. The solution are very stable. The particles of solute present in a solution do not separate out on keeping. A true solution does not scatter light because its particles are very small. What type of mixtures are separated by the technique of crystallization? Answer. The mixtures containing solids in which the impurities may be either less soluble in the solvent or more soluble in the solvent than the solids are separated by the technique of crystallization. For example, the impurities present in impure copper sulfate, common salt, and alum, etc., can be separated by the technique of crystallization to obtain the respective pure substance. To separate butter from curd. Answer is centrifugation. Name the technique to separate salt from seawater. Answer evaporation. Name the technique to separate camphor from salt. Answer sublimation. Thank you. As chemical change or physical change. Cutting of trees, chemical change. Rusting of almirahs is a chemical change. Passing of electric current through water and water breaking down into hydrogen and oxygen gases, chemical change. Next, burning of paper and wood is a chemical change. Next, melting of butter in a pan, physical change. Boiling of water to form steam, physical change. Dissolving common salt in water, physical change. Making a fruit salad with raw fruits, physical change. The things around you as pure substances or mixtures. Some of the things around us are tap water, milk, naphthalene balls, sodium chloride, air, gold ornaments, ice cream, steel, distilled water, diamond, steam, kerosene oil, alum, salt solution, brass, alcohol, vinegar, graphite, wood, and baking soda. We can segregate these things as pure substances or mixture. Okay, pure substances, naphthalene balls, pure substance, sodium chloride, pure substance, distilled water, pure substance, diamond, pure substance, steam, pure substance, alum, pure substance, alcohol, pure substance, graphite, pure substance, baking soda, pure substance. Next, mixtures. Tap water, mixture. Milk, mixture. Air, mixture. Gold ornaments, mixture. Ice cream, mixture. Steel, mixture. Kerosene oil, mixture. salt solutions, mixture, brass, mixture, vinegar, mixture, wood, mixture. How will you separate a mixture containing kerosene and petrol? Difference in their boiling points is more than 25 degrees Celsius, which are miscible with each other. Answer. If the difference in the boiling point of two miscible liquids is 25 degrees Celsius or more, their mixture can be separated by the process of simple distillation. In this case, the difference in the boiling points of two miscible liquids, kerosene and petrol, is 25 degrees Celsius. Therefore, a mixture containing kerosene and petrol can be separated by the process of simple distillation. This can be done as follows. The mixture of kerosene and petrol is taken in a distillation flask fitted with a thermometer and a water condenser. On heating the distillation flask with burner, the petrol having lower boiling point distills over first and collected in a suitable container. Kerosene having higher boiling point distills over later and collected in another container. Caution: petrol is highly inflammable. It catches fire easily. Thank you. Homogeneous and heterogeneous mixtures with examples. Those mixtures in which the substances are completely mixed together and are indistinguishable from one another are called homogeneous mixtures. A homogeneous mixture has a uniform composition throughout its mass. It has no visible boundaries of separation between the various constituents. A mixture of sugar in water called sugar solution is a homogeneous mixture because all the parts of sugar solution have the same sugar water composition and appear to be equally sweet. There is no visible boundary of separation between sugar and water particles in a sugar solution. A mixture of two or more miscible liquids is also a homogeneous mixture. For example, a mixture of alcohol and water is a homogeneous mixture. All the homogeneous mixtures are called solutions. Next, those mixtures in which the substances remain separate and one substance is spread throughout the other substance as small particles, droplets, or bubbles are called heterogeneous mixtures. A heterogeneous mixture does not have a uniform composition throughout its mass. It has visible boundaries of separation between the various constituents. The mixture of sugar and sand is a heterogeneous mixture because different parts of this mixture will have different sugar-sand compositions. Some parts of this mixture will have more of sugar particles, whereas the other parts will have more of sand particles. There is a visible boundary of separation between sugar and sand particles. The suspensions of solids in liquids are also heterogeneous mixtures. For example, a suspension of chalk in water is a heterogeneous mixture. A mixture containing two or more miscible liquids is also a heterogeneous mixture. For example, a mixture of petrol and water is a heterogeneous mixture. There are differences between homogeneous and heterogeneous mixtures. Homogeneous mixture has a uniform composition throughout its mass, but in heterogeneous mixture does not have a uniform composition through its mass. Homogeneous mixture has no visible boundaries of separation between the various constituents, but in heterogeneous mixtures has visible boundaries of separation between the various constituents. Homogeneous mixtures In homogeneous mixtures, the constituents of homogeneous mixture cannot be seen easily. But in heterogeneous mixtures, the constituents of a heterogeneous mixtures can usually be seen easily. What is meant by a pure substance? A pure substance is one which is made up of only one kind of particles. These particles may be atoms or molecules. For example, sulfur is made up of only one kind of particles called sulfur atoms. Therefore, sulfur is a pure substance. Similarly, water is made up of only one kind of particles called water molecules. Therefore, water is also a pure substance. In fact, all the elements and compounds are pure substances because they contain only one kind of particles. A pure substance is homogeneous throughout its mass. A pure substance cannot be separated into other kinds of matter by any physical processes. A pure substance has a fixed composition as well as a fixed melting point and boiling point. What produces more severe burns, boiling water or steam? Answer. When water changes into steam at its boiling point, it absorbs latent heat of vaporization, which is 22.5 into 10 to the power 5 joule per kilogram. This means that steam at 100 degrees Celsius contains much more heat in the form of latent heat. than boiling water at the same temperature of 100 degrees Celsius. So, when steam falls on our skin and condenses to form water, it gives out 22.5 into 10 to the power 5 joules per kilogram of more heat than boiling water at the same temperature. Since steam gives out much more heat than boiling water, it causes more severe burns. Why is ice at 273 Kelvin more effective in cooling than water at the same temperature? First of all, please note that the temperature of 273 Kelvin is equal to 0 degrees Celsius, and it is the melting point of ice to form water at the same temperature. Another point to be noted is that the latent heat of melting of ice or fusion of ice is 3.34 into 10 to the power 5 joules per kilogram. Now, ice at 273 Kelvin or 0 degrees Celsius is more effective in cooling a substance than water at the same temperature of 273 Kelvin or 0 degrees Celsius, because for melting each kilogram of ice takes 3.34 into 10 to the power 5 joules of its latent heat from that substance, and hence cools the substance more effectively. On the other hand, water at the same temperature of 273 Kelvin or 0 degrees Celsius cannot take away any such latent heat from the substance, and hence does not cool it more effectively. Thank you.